So before we go further, I'll just remind you again of Bayes' rule. We looked at this last time. The straight Bayes rule is that we can say that P of x given z, the P of the state given the measurement, can be written this way. This is the likelihood, all right? This is the total probability of z. That's our prior before the measurement. That's our belief, if you will, of what the value was, okay? So what's important here to realize is once I get the measurement, somebody gives you the measurement, you drove to Measurements R Us and you picked up your measurement. You didn't know which measurement they were going to give you, and there's a probability that they'll give you all these different Once they give you a measurement, the probability of having gotten that measurement is done. It is whatever it was. It's not going to change. So what that allows us to do is to sort of replace that by this normalization factor, right? It's some value. Or another way of saying this is that P of x given z is proportional to P of z given x, all right, times the prior. So if I had a whole bunch of different possible x's and I only had this value, okay, for P of x given z, they have to sum to 1. So what I could do is I could just take the sum of all of those, whatever they were, and then divide this value by that, divide by that sum, and I would be back to a renormalized probability density, all right? That's why we write it as this eta, we talk about this proportion. And in fact, next time when we do particle filtering, you'll see that what we do is we sample all these x's, we multiply them by their likelihoods, and we get all these values, but they don't sum to 1. So what we have to do is take all the sum them up, then divide each of those by that sum, and they'll sum up to 1 again.